video lecture is on bonding in terms of hybridized orbitals, thinking about how that relates to bond overlap and how we can explain some of these geometries by moving past just simple covalent bonds. Look at something that's a little more complicated. First of all, when you think about a covalent bond, you've got two atoms that are going to overlap their electron clouds to a certain point. They're going to overlap to the point that the repulsions don't become so great that they go apart. So when we see the overlap, that's sharing and mixing of these orbitals. When we think about it, how it looks here for hydrogen here on the left, see that these two nuclei, they're going to overlap to a certain point and share that 1s orbital. If you see hydrogen with chlorine, chlorine's outer energy level is the 3p, and it mixes here. The problem is this limits us to only really single bonds and explaining how these two atom structures work. So there's got to be more to it to try to explain it. So when you start getting these overlaps, you've seen this picture before, at some point when they start coming together, they start mixing. Nucleus repulsions get closer and closer and closer. Then there becomes this balance, which is the overlap. And then as they spread apart, it decreases. So what happens is this distance gets to a point to where the clouds mix and the repulsions are minimized, and there's a net attractive force where they don't repel from each other. Again, if they get too close, there is more repulsion from the nuclei from each other. And if they're too far apart, there's not enough mixing that happens between the two. So we have to decrease electron repulsion, and we've got to minimize the nuclei repulsion as well. So what is a hybrid orbital? Well, a hybrid orbital, the word hybrid means essentially to mix. If you think about this in genetics, you hybridize the two different genomes. Like in corn, you can have a hybrid of corn that mix the best traits of both varieties. When we're doing a hybrid orbital, we're talking about mixing together energy levels, or excuse me, orbitals, to try to make into a new orbital. That's a combination of the two. So this is an orbital diagram here of beryllium, 1s2, 2s2. Beryllium has two valence electrons. Its 2p orbitals are empty. They don't have enough electrons to fill into the 2p. When we think about hybridizing something, if we add a little bit of energy to this, what we can do is we can promote one of these electrons from the 2s into the 2p. This doesn't violate any of the electron configuration rules. It's still following Hund's rules, still following Pauli, still following Aufbau. It's fine because we still have the opposite spins and the quantum numbers. But we promote an electron up. So we can have two different bonds to form. If we left it just as this 2s with two electrons, those electrons are stable and happy. There's no reason for them to bond. But if we can promote another one up to the 2p, now we have two bonding sites that can happen. And that can help explain beryllium's molecular geometries. So when we mix an s and p orbital, we can mix them together to make what they call, they refer in the textbook as degenerate orbitals, hybrids of the two. This is an sp hybrid. How do you know it's an s and p? Well, an s orbital is spherical, p orbitals are dumbbell. So if I mix these two together, that's what the hybridized part means. We're going to have one lobe of the p orbital go with an s, and then we'll have the other lobe do the other part of the s. And once it mixes together, you have an sp hybrid. So you have the two lobes of the p orbitals here. One of the lobes is larger, more rounded, like in the s orbital. So if you start thinking about how beryllium and fluorine go together in a covalent bond, these degenerate orbitals will start to overlap. So if you notice here, the large lobes from these two sp hybridized mix with the electron cloud of fluorine's 2p. There's the overlap. There's the covalent bond. So this sp hybridized orbital mixes with the 2p of fluorine. There's the shared pair. There's the shared pair on the other side. Now this makes a lot of sense with the molecular geometry of beryllium for it being linear with zero non-bonded pairs. And it explains why beryllium makes two bonds instead of making none, because of the hybridization. Thinking about hybridization here, with beryllium, it would look more like this. We've combined one s orbital with one p orbital, and that's its own site for two bonding locations. If you notice, we have two electrons that are unpaired that can create bonds. A couple things to note here. The sp orbitals are higher in energy than 1s, but lower than the 2p. So it kind of takes the 1s and the 2p and mixes them into one in this in-between land. The reason they're called degenerate is they want to make bonds because they're unstable. So degenerate means break down or eventually make bonds whenever it works. We can also have sp2. Now it's important as you look at this 2 tells you how many p orbitals go with it, and the s tells you how many s orbitals. This has one s orbital and two p orbitals hybridizing. So we can have a total of 3 hybrid orbitals. So if you understand that the s has a 1 on it and there's 2 p's, combine that together and you get an sp3 hybridized orbital. This kind of is a good way to think about with boron trifluoride. If you think about boron and how it looks, boron, when you do its electron configuration, and I'll just do the valence set, it's got a 2s and then it's got a 2p. And the 2s has 2 electrons, you have 3 p orbitals, and it only has 1. So if we don't do hybridization, this would show that you would only have boron being able to make 1 bond, even though it has 3 valence electrons. So if we hybridize this into an sp2 hybridized orbital, we're going to mix these together and now promote 1 electron in each. So we took this 1 s orbital and we mixed it with 2 of the p orbitals to get an sp2. Notice we have 3 sites for bonding. Without this, we can't explain the 3 bonds. So that's an sp2 hybridized orbital to explain the 3 bonds that boron likes to make. So again, the sp2, the superscript, tells you how many of the p orbitals we have. Still a p orbital unfilled. That's one of our exceptions to our octet rule. And those 3 lobes would all mix together to make that sp2 hybrid. And that looks really similar to that trigonal planar shape that we saw with boron when it wants to make those 3 covalent bonds. Now, with carbon, when you look at it, it has an s orbital, and it's got an sp3 hybridization. Notice the superscript of 3. 3 p orbitals are going to mix with an s orbital to give us 4 hybrids, or 4 degenerates. So notice they have a p lobe with an s lobe, p with an s lobe, p with an s lobe, p with an s lobe, and they're all going to mix together, and notice that gives you the tetrahedral alignment. Let's think about how that works and how that gets promoted with the electron configuration. So if you look at carbon's outer level, if you just did the electron configuration by the rules, you would show those 2 electrons for carbon, and carbon would look like it could only make 2 bonds. So we have to have a theory to help explain why carbon can make 4 bonds with its 4 valence electrons. So we're going to take an s orbital, and we're going to take all 3 p orbitals and mix them together. So an sp3 hybridized orbital means we're going to take 4 total orbitals and mix them together into one kind of new super level, and we're going to distribute all 4 electrons one at a time in this new orbital, just like we would in Hund's rule. 1, 2, 3, 4. So now we have 4 bonding sites for carbon because we mixed together those 4 orbitals and distribute the electrons. It's unstable, and it bonds together, and this accounts for this geometry that we talked about with the tetrahedral shape. There's the 4 bonding domains around it because we have 4 orbitals that can overlap and share valence electrons. So this hybridization is really kind of the key to explaining a lot of chemical bonding. And the way they overlap can explain a lot of the chemical behaviors. A couple of things to think about before I leave you. when you're trying to figure out this hybrid orbital business, if you want to try to determine what they are, the first step you need to do is you need to determine a valid Lewis diagram. That's the first step. If you determine a valid Lewis diagram, that's going to help give you an idea about where the bonding sites are. 2, use the Vesper model to determine the electron domain geometry around the central atom. And then specify the hybrid orbitals needed to get this done. So we're using the theory to explain the observations and how that looks. So, for example, if we were thinking about the hybridization here, they show you in your textbook about how it looks for NH3. It's one of our examples. If you did your Lewis diagram for NH3, you have four electron domains. So there are essentially 4 sites in and around that hydrogen where there can be bonds. If I have 4 electron domains, I'm going to have 4 hybridized orbitals. I have to have 4 hybridized orbitals to make this happen. So if I only have those 4 domains, there's no way I'm going to be able to show. I've got to have those 4 orbitals to make it happen. So if you think about nitrogen and how it looks, you've got your 2s, you've got your 2p, and it has 1 electron in each. Well, that only shows that it has 3 bonding sites. So what has to happen in order to accommodate those is they have to go together into an sp3. So we get 4 orbitals and we distribute those electrons into all of those. That's the hybridization that has to happen. That accounts for bonding site 1, 2, 3, 4. Without it, we can't get that done. So we have to have the hybridization to help explain the geometry of it. So the electron domain geometry is really important to help explain that. We'll talk more about sigma bonds and pi bonds a little bit later and work out a couple more examples of this in class. We'll continue to build the models, which I think are helpful, and then explain more of these sigma and pi bonds as we move on. Thanks for watching.